Okay, so we're going to talk a little bit about equilibrium, which will be really the focus of our whole last marking period, but we want to relate equilibrium to Gibbs free energy. So equilibrium is not a really difficult concept, so we can just go take a few minutes here. This is not in your notes, so again, you can write it in your margin, or you can just listen. I talk about it relative to what's on page 24, which is where it talks about the Ratlink equation. Okay, so equilibrium means that I have the rate of a forward and a reverse reaction that are exactly the same. Okay, so here's what it looks like. If I have a forward reaction where I have concentration of reactants going away, and the reverse reaction where the products are going away, we are at equilibrium when we reach the point in purple here where the rates of the two are the same. So when we're at equilibrium, the reaction doesn't stop, but in fact reactants are being converted into products, and products are being converted into reactants at the same rate. So what you'll see overall is the concentration of reactants and products are not changing. Okay. And the calculation for the equilibrium constant can be taken right from the balanced stoichiometric equation. And so K, this is big K, and we're using concentration here, so Kc is what we're calling it. It's the concentration of the products raised to their coefficient over the concentration of the reactants raised to their coefficient. Okay? And the magnitude of K indicates the extent to which a reaction goes to completion. So most of the reactions we've been talking about so far, we talk about them as though they go all the way from reactants to products. But in fact, a lot of equations or a lot of reactions don't do that. They end up somewhere in between, going back and forth. So if K is much less than 1, that means the reaction has not gone forward very far, and I have mostly reactants remaining. If K is much greater than 1, then mostly products are being formed. So this is the equation that relates delta G and K. It also relates E, which we'll talk about when we get to electrochemistry. But it's this equation that we call the Ratlink equation. Gibbs free energy, the change in Gibbs free energy is equal to the negative of RT natural log of K, the equilibrium constant. So R, this R, we are using the energy R, which is 8.314 joules per mole K, which you have on your equation sheet. You just need to know that this one is the one that's used. And whenever we're dealing with energy, we're going to use this R. Temperature is in Kelvin, and of course Ln is the natural log. Okay, so we're going to skip ahead to problem 21. Alrighty. For this one, for the overall reaction, we want to find the equilibrium constant. So we need to find K. So the reaction that we have, the equation that we have that uses that is delta G is negative Ratlink. So go ahead and try it, and then come back when you're done. Okay, so delta G is negative Ratlink, and then I can also use delta G is minus delta H T minus T delta S. Okay? So I wrote really small here, and I apologize. You probably can't see it, but I'm first calculating delta H using the table of values. Then I calculate delta S using the table of values. I calculate delta G using delta H equals minus T delta S. Once I have my delta G, I plug that into the Ratlink equation and calculate my K. Alright. So when I did that, just to sum up, I ended up with a delta H of minus 165.2 or 1652 kilojoules per mole. My delta S was minus 0.53 joules per mole K. My delta G, when I plugged it into delta H minus T delta S, and I had to change my delta S units, right, by multiplying times 10 to the minus third. I plug them into the delta G equals negative Ratlink, and this is probably the one area that people are most likely to make a mistake, is delta G is kilojoules my R value is 8.314 joules per mole, joules per mole K, so I need to change that to kilojoules to make it work. Alrighty? And let me just make sure. Oh, the really disappointing thing is you may end up with getting a overflow error on your calculator because the K is enormous. So you should have ended up with K equals e to the about the 601. So K is about 10 to the 260th. Just some huge number. Okay, the important thing is that you can follow the steps. Alright, here's another one. We want to find the Gibbs equation can also be used to calculate the phase change temperature of a substance. During a phase change, the system is in equilibrium. So the delta G is going to be 0. Okay, so it's asking us to calculate the thermodynamic boiling point, which is the temperature, given the information below. So if it's boiling point, key word, boiling point tells us we are at equilibrium, right? We're in equilibrium, and delta G equals 0. So delta G equals delta H minus T delta S. I set delta G equal to 0. I rearrange the equation by adding T delta S to both sides, and I get this. I solve for T, which is delta H over delta S, and I get 44 kilojoules per mole. I've got to adjust the delta S by using the 10 to the minus 3 to get it to kilojoules, and I get a value of 370 K. That's my boiling temperature. Alright, here's, I think, the last one. Alright, for the reaction of CO2 plus oxygen, carbon monoxide plus oxygen to yield carbon dioxide, I have my delta G, and we want to calculate K, the equilibrium constant. I'm going to use RATLink again and solve for log of K. And when I do that, remember my delta G is in kilojoules, my R is in joules, so I got to change it. Okay, this is moles K, and when I do that, I get 298 K. Oh, times 298 K, my bad. And then I multiply it out, I get K equals e to the 103, which is about 1.2 times 10 to the 45th.